Hi, my name is Jason, and I'm simulating three different types of flow. I'm simulating Poisson flow, Coyette flow, and then a combination of the two. So in order to start, we bring over one of these fluent things. You go into geometry. We make sure that it is 2D, and then we go straight into it. Everything takes forever to load. This video is going to be like 30 minutes long, just because nothing loads. That's the wrong one too. Good thing this isn't my storage. Someone up in Design Modeler instead. Alright, so we're gonna focus on that XY plane. So we isolate the Z, go over here, start sketching. Since it's only 2D, we're gonna sketch technically a rectangle in this manner. And we're going to put in some dimensions for the vertical component. And then the horizontal component. So here, we gotta make sure that our units are in millimeters. Our horizontal component is going to be 750 millimeters, and then our height will be 5 millimeters. To ensure we're following the rules inside of the document given. So after we're given this, go to this drop down, go to our sketch. We can, I think we generate it once. And then we go to concept, make a surface from the sketch. Here we have that, and then we generate this surface. Gotta make sure that our object is selected too. Can I select my object? Why isn't this working? Delete. Go to our sketch. Make a surface from this sketch. Apply. And then generate. So now we have our body. And next, we want to then go to our mesh. It should have already updated. Now we wait again. Here we have our sketch. Go back onto the XY plane. And then we start analyzing this mesh. So the best strategy is to go into insert, insert and start messing with the sizing. So here we want to divide these into different sections across both the horizontal and vertical way. We can choose which way we select items. So we go to cursor edge, and geometry, we want to apply it to just the edge. while holding control, one edge, maybe. Hold on, let's delete this. It's generating do anything. Interesting, okay. Now I wanted to do method, that's what it was. Automatic method, click on our surface, apply, create another mesh, insert sizing, and then apply it to just the edge, just these faces, holding control, clicking on both halves. Please. Apply. Go to our type, switch from element size to number of divisions. Ignore that error. Put in, I believe 100 will work. Generate. Here that works. We also forgot to make this a hard surface. So regenerate again. It's ready, and now we have to make our second division with sizing. We're going to do the top and the bottoms now. Holding control, clicking, apply, same thing. Change from element size to number of divisions. Make this 500. And then make this hard. Generate. And we should almost have our surface. We just need to do once more face mesh. Select this, apply, and then generate. Okay, so I think once we click out of this, we should see our divisions. That looks about right. Go back into our document, update this task, and then head straight into setup while using double precision and selecting start. You can have a few pop-ups. Okay, here is our technically 2D pipe where we want to start manipulating our variables. Here we have our fluid that we want to edit, and the density that worked best for me was 1 kilogram per meter cubed, and then the viscosity, the best one was this number. Change and create, close item, and then now we want to manipulate which mode it is. We're trying to consider laminar flow, so we want to look up in here for, is it in here? Yeah, laminar flow, click OK. And then now we can start manipulating our velocities and boundary conditions. So since we're trying to simulate Poiseuille's flow, we have to manipulate the, oh, I did forget a step. Okay. First, we actually have to go back here and then rename a few things. So we want to rename each edge. So top edge is going to be called upper wall. Lower edge is going to be called lower wall. Side edge is going to be called the inlet, and then the other side will be the outlet. Okay. Generates kind of like a refresh button to me. Here we want to update our mesh. saying we'll update our setup. Hopefully. If you close this window, yeah, hold on. Close. Okay, open up setup, edit. Yes, load new mesh. Double precision, start. Oh my goodness. Let's make sure our fluid is proper, yes. And our model is laminar. Okay, now we can mess with the boundary conditions. Here, our inlet is, we want to manipulate the velocity. The one I chose and worked best for me was 10 meters per second. And then we just want to make sure that our outlet is based on absolute pressure, no addition of anything. Then we want to make sure our walls are stationary, which it looks like both walls are. Yep. And then that should be it. That we can start. We want a number of iterations. I'm going to choose 100, initialize, and calculate. Here we're plotting our iterations in the residual. Here the calculations, and then these don't make too much sense until we add vectors. So here, put the style, it's going to be the vectors of the velocities, and then we're going to select all of these to plot. Save and display. And then here we actually see the simulated flow with P+C. The inlet flow is, it starts off unsteady and then eventually the center becomes faster. I don't know why this is buffering. Okay. Starts off slow and dispersed, and then as soon as it goes on, the velocity grows in magnitude. And so this looks about right. What we can now do is go into our results, edit our results, and then start manipulating some values to find whatever we need, such as the tables and the charts. So here, back onto the y-x plane, and then start looking for we want to add that contour. So we can start by inserting a contour and call it vector magnitudes. And here the location is going to be across the symmetries. The variable will be velocity u, and then the range, yeah, global. Number of contours, we want to increase this number so it looks great. And domains, yeah. Apply. We also, if it's possible, no, that's alright. What we see here is the contour of the velocities. At the edges it should be near zero, and then in the center we'll have the maximum velocity. So this is one of the contours, and then now we want to chart the velocities against the height of y at midpoint and endpoint. So before we do that, we have to make a location for these midpoints and endpoint. So this will be the midpoint. This will be a line from halfway through, so the length of my rod was 0.75, 750 millimeters, meaning we would go halfway. So this is our x coordinate. This would be our y coordinate. We want to range it from 0 to the top, which was only 5 millimeters. Sample. I think we can increase the samples. Apply. So here we can see the line at the midpoint, and then we want to do the same for the endpoint. And here we have a problem where we want to start with our same height, but we want to make sure that we go a little before the very end to be able to plot it properly. This will be also 100. Apply. Let me see that at the very end. Now what we can do is insert a chart here. We'll leave the title of chart 1, where we can graph, where we want to find the velocity, the maximum velocity plotted against height. Then here, pick data series 1, location, we can find at the midpoint first. And then we make a new one to find it at the endpoint and plotting them against each other. So here, the x-axis, we want it to be the velocity. And the y-axis, we can make it the y height. Here we apply, and we should get a graph similar to this. Since it's laminar flow with a low Reynolds number, these graphs will look quite similar. But you can tell between the differences that the velocity increases as the length goes on, such that that's what the Poiseuille's flow does. And the last thing we want to do is, in order to find any of the velocities, we can export the information that we find, export, and then go into Excel later on, making sure that here we highlight the information we want to know, which is the velocity of u, and then the actual height. Doing so will allow us to find the maximum velocity later on. Just opening up an Excel and finding the maximum values. And then in order to do this for the Coyette flow and then the mixed flow, all we have to do is, let me make sure that we can just go back into these values and change this information. And now in order to do it for the Coyette flow, all we have to do is go back to this part of the simulation. So with the Coyette flow, the way it differs from the Poiseuille's flow is that there is no initial velocity or inflow from, there's no momentum from that. They start off with momentum coming from the walls moving. So here, we want to do is edit the inlet to make it a pressure inlet. This will cause it to have a zero pressure difference. Same thing at the beginning versus the end, like initial. So applying this allows that to fix that problem. And then we want to move our upper wall. and we're going to make this a moving wall. And the speed that I found worked best was 20 meters per second. Apply that speed, close. No, it was 50 meters per second. My mistake. 50 meters per second, apply and close. And what we can also do is manipulate other variables to ensure that our Reynolds number is lower than 2500. So that allowed me to change the viscosity of the air to only 0.008 kilograms per meter second. Change and create, keeping the density. And with these changes, we should be able to initialize and calculate. And here we have this velocity. We should be seeing a linear line in our graph when we update it. Here we can refresh the simulation.
Because I don't know what the actual, if that 0.001 is the actual viscosity.
And then we see basically a linear line. There's a few errors coming from my end, but it is basically linear. Below you should see the series. If you can see right around this area, you can see a little bit of it. The midpoint versus the end point. And that is how we do that thing. And the next is to manipulate and find a combined mixed flow of the two. So here, the only thing that we do different is we just change a few numbers. The wall velocity, we're going to make 20 meters per second. Apply. And then we're going to make the inlet velocity. We're going to change this to a velocity inlet with a velocity of 30 meters per second. Apply and close. And then our viscosity is going to change, possibly. And then we basically run it again after we change the velocities. Doing so will give us this graph. I had already run it, but it gives us this velocity. We should see the combination of the flows where we have the Poiseuille, the inlet flow, coming in this fashion towards the middle, and then we have the acceleration or the velocity coming from the moving top wall. And so we end up getting a graph that looks like this, rather than that straight line. Here we see that maximum velocity is around 0.003 3 millimeters, and the height a little lower. And that's really about it. Besides, like I said earlier, exporting the data, we can export it and then find these actual values from looking at the tables. But I think that's about it. Thank you.